Under decimal. Yesterday we did adding, correct? Adding / subtracting. We do that again today, except the little subheading under the subheading is working with whole numbers. And you'll remember the little phrase that pays when you add, subtract decimals is to do what, Riv? Line them up. Line them up. But the difference is what right now is what happens when there's a whole number. Let's say I have 8 minus 3.5. Rather than panicking here, why? Because there is no decimal in 8. How am I going to line up a decimal in 8 if there's no decimal there? We are going to solve our own problems here, Aiden, by?
Put a 0 behind it.
That makes it 80.
8.0.
Alright, you, and write this down, you can always put a decimal after, in capital letters, the whole number. Not before, that would make sense, but after the whole number. So like Aiden was saying, I do 8, I put the decimal there, and then everything is going to line up with that decimal. This becomes 3, or stays 3.5. Then my answer, the decimal, is going to go there. Feel free to put your 0 there to add and fill in. 5 from 0 can't do, so I borrow. This becomes 5 from 10, and 3 from 7 is 4.5. Are we on the same proverbial page there?
Yes.
Do I need to beat that horse anymore? Beat the dead horse anyways. It's a phrase. Doesn't help to beat the dead horse because he's already dead. Got that? Alright, then, now blank piece of paper. Because we have to talk about exponents. So much to talk about, so little time. Let's say I've got 5 squared. 5 to the second power. Everybody there? You're about to take a flurry. I repeat, a flurry of notes. First of all, let's put down some names here. This little 2 up here, it is what we call an exponent. It is also known as a power. And this 5 right here, the big number when you talk about exponents, is called the base. Unless you think that you know what the answer to this is, it is definitely not 10. Here is what exponents tell you. The exponent tells you how many bases get multiplied together. Exclamatoria al punto. The exponent tells you how many bases get multiplied together. So here's what that looks like. 5 squared means that you have 2 5s not added together but times themselves. So the answer is not 10. 5 squared is 25. 5 times 5. 5 to the 3rd power would be 5 times 5 times 5, and 5 times 5 times 5 is, John? 125. Let's keep her rolling here. What about 5 to the 4th power, which is 5 times 5 times 5 times 5? Anybody got that math? Oh, Lily's thinking. Riv? 625. And then let's go one more just for fun. 5 to the 5th power is 5 times 5 times 5 times 5 times 5. Ooh, people are Aiden did a paper, but I'll give you that. What'd you got?
3,125.
3,125. Oh, why not? Let's go 5 to the 6th power.
Yeah.
Which is 6 5s times themselves. Which really shouldn't be that bad, people, because 5 times 3,000 is 15,000, correct? We already did 5 times 125 right here. So putting the 15,000 together with what we did right there, you end up with, River? 15,625. Now, what you will notice here, boys and girls, is that, you know, these are not, 25 is not really a big number, and 125 is not a big number, but as you keep going a little higher in the exponents, look at, I mean, this goes from 600 to 3,000, 3,000 to 15,000. The next one's going to jump up to about 75,000. And then the next one after that's going to jump up into the 350,000 category. And the one after that's going to be in the millions. That is what, if you ever hear somebody talk about exponential growth, that is what they're talking about. A lot of times they talk about it in exponential. How about exponential? Exponential growth. Mrs. Stone might talk about it when she talks about bacteria growing. Bacteria grow exponentially, which means you only need one little bacteria to start off with. And that's not going to really do you much damage. But bacteria, what happens to bacteria is it splits into 2. And then after 2, those 2 split into 4, and then those 4 split into 8, and those 8 split into 16, and then, you know, it starts out really slowly at first, but when you start splitting 16 and get 32, and then 32 splitting and get 64, and then 128, you know, and when you get to the end, they start doubling. You double enough times, you get crazy doubling, and that's exponential growth. So if you hear that exponential growth, that's why they talk about this. Now, a couple special things. Let's talk about this. We didn't talk about this, but 5 to the 0 power. Everybody always guesses. Very few people ever guess right. 5 to the 0 power, Aiden? It is not 0. Brady? 5. It is not 5. Nobody ever gets it. Anybody? Ellie? Huh? It is not 10. Get one more and then we'll go. Brody?
15.
It is not 15. 5 to the 0 power is 1.
Oh, that's what I was doing.
Which you can write down anything. I repeat, anything to the 0 power is 1. Anything to the 0 power, whether it's a number, a letter, or anything. You can have 1 million boys and girls and children of all ages to the 0 power, that equals 1. Okay? And then anything to the 1st power, or 5 to the 1st power. You might get this one, I don't know. Anything to the 1st power of the guesses, Jonah?
5.
It is. Yep. Anything to the 1st power is itself. anything to the first power is itself. Anything to the 0 power is 1, anything to the first power is itself. And then just a couple other little minor housekeeping details. Just with these two special ones, an exponent of 2 is usually not called 5 to the 2nd power, but an exponent of 2 we usually say squared. 5 squared is 25. We don't usually say 5 to the 2nd power or 5 to the exponent of 2. And the same thing with 5 to the 3rd power. We usually don't say to the 3rd power. If it's to the 3rd power, we usually say, Ellie? Cubed. No other exponents have 5 to the 4th power is just 5 to the 4th power, 5 to the 5th power is just 5th power. You don't have to say anything except those are the ones you say squared, cubed. Everybody's happy with that? Yep. Perfect, blank piece of paper. Along the same lines, the opposite of exponents and powers are what we call roots. Oh. In particular, today, we are talking just about square roots. And square roots look like this. Understand very clearly that this is not a division problem. This is not a division sign. It would be if it didn't have this little thing in front, but it has the little heartbeat monitor thing there. This is what we call a square root. And the way you would say this is, you're looking for the square root of 36. That's how you would say, if you see this little hole, that's what it is. Well, this little symbol / sign right there is called the radical sign. It is radical. And this number underneath the radical sign is called the radicand. Again, didn't make them up, just tell you what they are. Radical sign, radicand. Okay? And the question, the answer, the simplified form of the square root of 36 is this. You have to ask yourself, what number times itself gives you the radicand. That is what that whole radical sign means in this case. So if you are looking at the square root of 36, you have to kind of think about it this way. What same number times itself will give me 36? And there is no magic formula for this. This is simply by trial and error. I mean, you can go through the list. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. Lily?
6.
Right. 6 times 6 gives me 36. So the square root of 36 is simply 6. It is just 6. Okay? Now the unfortunate thing about square roots is there are only a certain amount of them that actually work out. For example, let's write these down. The square root of 1, the square root of 2, the square root of 3, the square root of 4, the square root of 5, the square root of 6, the square root of 7, the square root of 8, the square root of 9, and the square root of 10. Let's look at what the answers to these may or may not be. First one, the square root of 1. What number times itself gives you 1? Jonah?
1.
1. So this is 1. The square root of 2. What number times itself gives you 2? Ellie?
1.
1 times 1 is 1. We already did that one. Somebody want to help Ellie out? Rib?
Number.
Yeah, you can't do this. It's a decimal number, and believe it or not, it's what we call an irrational number. Because if you plug that actually into a calculator, you get a decimal that never ends. Kind of like pi up there. It would go on forever if the calculator could go on forever. The square root of 3, what number times itself gives you 3? Rib? Can't do it. How about 4? What number times itself gives you 4, John?
2.
2. So there is a square root of 4. 5, no such thing. 6, no such thing. 7, no such thing. 8, no such thing. Well, there's again, it's a long decimal. Square root of 9, though, Brady,
3.
is 3. And the square root of 10, no such thing. These things right here, children, these ones that work out are what we call the perfect squares. And there's not that many of them compared to how many there's not. I mean, all these x ones aren't perfect squares. We got a ratio right now of what, about 3 to 6. It doesn't keep up that same thing. But let's think about this. What are the rest of the perfect squares up to whatever? Let's do the next 7 of them. After the square root of 9, what would be the next perfect square you come to? A helpful little thing here is look. 1, 2, 3. This is 3 times 3. The next one, Brady, is going to be the square root of what? 16, because that's what that is 4. After that, the next square root would be, Anna?
25.
Yep, square root of 25, and that is 5. And the next one would be, Brady?
6.
36.
Yeah.
Which is 6. We did that. Then, Ellie?
49.
49, which is our 7. Then Aiden? 64, which is 8. Then Jonah?
81.
81, which is 9. And rounding off the top 10, square root of John? Which is 10. And you could keep going. Anybody know what 11 times 11 is? Rip? 121. Most people know what 12 times 12 is. Norquist? 144, and that's 12. But you can see they start to get few and far between. Look at how many square roots between 121 and 144 that don't work out. Square root of 122, 123, 124, 125, 126, 127, 128, 129, 130, 131, 132, all the way to 144. Most of them don't really work out. Fortunately, your math book is nice and it gives you most of these ones that work out. And those are the perfect squares. Perfect squares. Perfect, you say. All right. Ladies and gentlemen, you have achieved semi-greatness. And that was all one lesson. Did you do that?
That was
That was brutal.